In problem number 1, student mixes 100 milliliters of 0.2 molar chemical A with 100 mils of 0.2 molar chemical B in a coffee cup calorimeter. To determine the total heat, we use Q equals mc delta T, and to find the mass, we use the density of the solution. Since density is equal to mass divided by volume, the mass would be equal to 1 for the density of water, or we're assuming the solution is the same, times 200, because there are 100 milliliters of each solution, for a total of 200, or 200 grams. Putting that into the equation, 200 grams times 4.184, the specific heat of the solution, times the change in temperature, temperature final minus temperature initial, gives us the heat in joules, which is 3,347. It's lost, so it should have a negative sign in front of it as well. Molar enthalpy means per mole, and in this case it's per mole of solution or chemical B that they're asking for. And so we need to take and divide our energy by the moles of chemical B. To find the moles of chemical B, we use the molarity triangle. Moles are equal to molarity times liters. Our molarity is 0.2 molars, our liter is 0.1, so we end up with 0.02 moles. Dividing those two animals, we end up with 167,360 joules per mole for number 1. Number 2, look at the reaction below. It has the standard enthalpy change. And it wants us to determine the enthalpy of formation for NO. For this equation, or for this reaction, we know that the enthalpy of the reaction is equal to the summation of the enthalpies of formation of the products minus the summation of the enthalpies of formation of the reactants. It's always products minus reactants. And in this case, our products are O2, which is 0 because it's a substance in its standard state, and then NO2, which we're told has an enthalpy of 50 kilojoules per mole. So those are our products. Minus the reactants, O3 is 300, plus NO, our substance that we want to know. And it tells us that the overall enthalpy, or delta H for reaction, is negative 200 kilojoules per mole. Solve that for NO, and you have your standard enthalpy of formation for NO. The reaction below contributes significant to smog. Calculate the quantity of heat released when 80 grams is converted to NO2. First, take your number of grams and convert it to moles. Put grams in a position where it's going to cancel. Moles is your new set of units. This is the substance NO. Nitrogen is 14 and oxygen is 16, so I believe it adds up to 30 grams. And then we can use the stoichiometric relationship in the equation between NO and delta H, or our number of kilojoules right here. There are 50 kilojoules released for every 2 moles of NO that are reacted. And this will give us our quantity of heat in kilojoules that are released. It will have a negative sign in front of it because there's a negative sign right here. Complete combustion of 36 grams of pentane releases 1,000 kilojoules. Write the balanced equation. Pentane is C5H12. Oxygen is added to that to make combustion. It makes CO2 and H2O. To balance this, do the carbons first, then do the hydrogens. Lastly, do the oxygens. There are a total of 10 plus 6 or 16 oxygens, so we need an 8 right here. On the basis of this information, calculate delta H for the complete combustion of 1 mole of pentane. So for every 36 grams of C5H12, there are 1,000 kilojoules of energy released. So first we need to convert this to moles. Put grams in a position where it's going to cancel. Moles is our new set of units. Every carbon is 12. We'll have to multiply that by 5. And then each hydrogen is 1. So we'll add 12 more to that. That will give us our total number of grams. And this will give us our moles of pentane, C5H12. And we want to know the delta H for the combustion of 1 mole of this. And so we'll take our energy now, 1,000 kilojoules, and this is how much energy this released, so there's a negative sign, in this many moles right here. And if we want it per 1 mole, we'll divide those two numbers, and we'll end up with kilojoules per mole, which is 1 mole of substance.